Sensible heat effects. The history of sensible heat, back to early studies in thermodynamics calorimetry, T refers to the heat exchanged by a body or system that results in a change in temperature, without altering other macroscopic variables like volume or pressure. Joseph Black, a Scottish physicist and chemist, is credited with distinguishing between latent and sensible heat while studying heat transfer during phase changes. He demonstrated that sensible heat is the heat that can be felt and measured by a thermometer, unlike latent heat, which is involved in phase changes without temperature change. Joule's experiments showing that work could convert directly into heat, marking heat as a form of energy rather than a material substance. Definitions of sensible heat and sensible heat effects. Sensible heat is the heat that can be felt because of its energy moving from one system to another that changes the temperature rather than changing its phase. Sensible heat effects refer to the temperature change in a substance when heat is added or removed without causing a phase change. The standard equation for sensible heat is Q equals mc delta T, where Q is the sensible heat, m is the mass of the object, C is the specific heat of object, and delta T is the change in temperature. The key thermodynamic variable is temperature. With molar or specific volume chosen arbitrarily, we have U equals U TV, then we got this below equation. First, constant volume heat capacity equation CV equals del U over del T constant volume. Second, substitute this equation 2.15 into the previous internal energy equation. Third, the final term is zero in circumstances for any closed system constant volume process and whenever the internal energy is independent of volume, as for the ideal gas state and the incompressible liquid. The heat added equals the change in internal energy. For a constant volume process, this can be calculated by integrating the specific heat at constant volume over the temperature change. The enthalpy may be treated similarly, with molar or specific enthalpy expressed most conveniently as a function of temperature and pressure. Then H equals H, Tp. Constant pressure heat capacity equations shown below. Then, substitute equation 2.19 into the previous equation. Again, the final term is zero for two situations, which for any constant pressure process and when the enthalpy is independent of pressure, regardless of process. Thus, Q equals delta H for mechanically reversible, constant pressure, closed system processes. Temperature dependence of the heat capacity, given by empirical equation below, where alpha, beta, gamma, A, B, and C are constants. Therefore, we obtain equation 4.4 below. Heat capacity in the ideal gas state. The basic equation for the temperature dependence of the ideal gas state internal energy is shown. Temperature dependence is expressed analytically by equation 44, where value of constants are given in table C.1 of. Appendix C. Evaluation of the sensible heat integral. Integral Cp dt is accomplished by substitution for Cp as a function of T by equation 4.8. Factoring T to T naught of equation 4.8 gives square brackets as Cph over R. In equation 4.9, where Cph defines as mean heat capacity for temperature range from T0 to T. Therefore, equation 4.10 were obtained. Solution for equation 4.10 for T gives equation 4.11. Iteration continues to convergence on a final value of T. Example for sensible heat effects. Calculation by using MATLAB application. An ICPH equation were used.